introducing the first keynote of the conference, it is my pleasure to introduce our speaker, Professor Katrina Ligett. Katrina is a professor of computer science at the Hebrew University of Jerusalem, where she also directs the Interdisciplinary Federman Center for the Study of Rationality. Her research explores how we can make good and responsible use of data, bringing together ideas from computer science with disciplines including economics and law. Her work has advanced both the algorithmic foundations and our understanding of what is possible in data privacy and algorithmic fairness, and has helped shape how we think about protecting sensitive data while still enabling learning from it, and about designing algorithms that are both effective and fair. A few words about her career. So before joining the Hebrew University, she was at the faculty at Caltech. She earned her PhD from Carnegie Mellon University, and she completed a postdoc fellowship at Cornell. Katrina has received numerous honors, including a recent ERC Consolidator grant. And I'm very pleased to welcome her. So please join me in welcoming Katrina, who will present her keynote named Data Degrades with Use. Katrina, please go ahead. Thank you.
Thank you so much. Thanks for the introduction. I really wish that the reality were different and we were meeting in person in Dubai, but I want to congratulate the organizers and thank them for a really graceful transition to online. You've all done a lot of work and it is very visible. So today I have kind of a provocative claim that I want to share with you. I want to argue that in some sense we've been thinking about data wrong, and I include myself in that we. And I want to claim that this wrong thinking has consequences. And then I want to explain what's wrong with our thinking, and I want to share some alternative ways of thinking about data. The two motivating contexts that I'll explore with you today are related first to privacy and second to statistical validity. But the tools that will inform our perspective today are really diverse, ranging from economics to law and, of course, computer science. And the consequences, I think, are just as far-reaching. So we, for years, have been hearing about the data fire hose. And we often treat data as this infinitely reusable resource. We think about a single data set as being able to support many, many, many different analyses. We use the same data to train multiple models. And we think about data as something that we can share widely without apparent cost. Now, economists, when they talk about data, often emphasize the ways in which data differs from traditional goods, like, say, an apple or maybe a pair of shoes. And they'll tell you that data, unlike shoes, can be copied nearly for free. And they'll emphasize that data can be used and reused as many times as you want without degradation and without consequences to future uses. And these aspects of its sort of economic characteristics have significant impact on how we should think about and use and govern data. The intuition behind all of this is that it feels like data has more in common with, say, digital music than it does with an apple. And the hope is that data can and should be widely shared, that data is a valuable collective resource, and the more we share it, the more we use it, the more discoveries can be made and the more problems can be solved. And there's also a really prevalent approach right now that views widening access to data as key to various antitrust concerns. The reasoning goes that if data is really valuable in certain marketplaces and gives a market advantage, for example, in web search, if what we want to do is we want to level the playing field and allow competitors to enter, then perhaps we should force the dominant players to share their data in some way. And the reasoning goes, this should only make things better for the common person. Now, I'm not blanket always against data sharing, but I want to share some caution today. Okay, before we dive in, what do I mean by data in all of this? My language around data is going to be very, very general. For me, data is really anything, whether it's structured, semi-structured, unstructured information, can take many forms, whether you want, video or text or various other forms of measurements. You can think about data as encoding insights about individuals, about society at large, about the world, about nature, about business opportunities, scientific discoveries. So for me, data is extremely, extremely general. And what I want to do with you today in our discussion about data is to share two different perspectives that each of them bring some caution about why the data doesn't degrade, or the non-degrading model of data, or the use data as much as you want freely model of data is problematic. So I'm going to start with a privacy perspective, and then in the second half of the talk, we'll move to talk more about statistics and statistical validity and doing good science on the basis of data. So first, the privacy perspective. Now, for this part of the talk, we're going to presume that privacy is something we care about, or at least we're required by regulators to pretend we care about it. So go with me here. Even if you don't really care about privacy, at some point you're probably going to have to use some data that comes with some privacy concerns. And anyway, the tools for thinking about and using data while respecting privacy, they end up being pretty useful for other purposes as well. So even if you're not a dedicated privacy researcher, come along for the ride here. So the background to this privacy discussion is that over the past couple of decades, there's really been a revolution, a significant set of developments in our formal mathematical understanding of privacy. So the notion of differential privacy that comes out of foundational work of Denor and Nissim and DeWork, McSherry, Nissim, and Smith is a concept that gives us basically a formal, rigorous mathematical vocabulary for exploring how and when we can protect intentional releases of various sorts of aggregates, whether they're statistics or training machine learning models or producing synthetic data. And when we can do those intentional releases in a way that avoids accidentally revealing too much about the individuals on which we base those releases, so on the underlying data. I'm not going to get into too much detail about the differential privacy model. This is not going to get very technical, but I think the model itself offers some useful guidance for our thinking, and also some parallel work in the field of privacy is going to be really important for our discussion today. So just for a little bit of background, differential privacy really has blossomed over the past couple of decades. And at this point, the literature offers many different models under which we can do many, many different types of computations while giving formal guarantees of privacy. So we know both how to release many, many different aggregate statistics on the basis of sensitive data. We also know how to do various sorts of machine learning on the basis of sensitive data, with the guarantee that the models that we output are privacy preserving, that they don't, for example, encode the training data in some subtle way. We know how to do more online privacy preserving query response. So we know how to answer requests that are formulated over time by various actors, potentially colluding in some way. We know how to take a sensitive data set, and we know how to create synthetic data that respects key aggregates of that data set. And the magic of synthetic data is once you create it in a privacy preserving fashion with formal mathematical guarantees, then you can publish that synthetic data, and anyone who wants to can use it for whatever they want, and the privacy concerns don't get worse. The privacy harms don't further accumulate. You've already paid for privacy in creating the data, and every subsequent computation comes basically for free from a privacy perspective. And we also know how to work with privacy in a model where actually individual data providers don't trust some central curator, but instead they provide their own privacy, for example, on device. And this is the model of differential privacy that's typically implemented, for example, on your cell phone to protect the specific things that you're typing in your text messages, while still allowing large companies to learn things about trends, what emojis are popular, make predictions about what you want to type next, so you have those convenient predictions on your keyboard. So basically, intuitively, what is differential privacy guaranteeing as a privacy notion? The idea is that any two similar databases should produce similar outputs. So differential privacy is a constraint on the behavior of our algorithms that take in sensitive data. And it's a constraint that says our algorithms need to produce similar outputs when they're fed similar data. We'll make that a little bit more specific here as we go along. So in particular, we're going to use the notion of similarity of databases that says if two databases differ by the addition or removal of one person's data, and that's any two databases that differ by the removal or addition of one person's data, we want to give this sort of guarantee of similarity on the outputs of our algorithm, but we want a guarantee of similarity that's going to be really general. We don't want to restrict ourselves to only talking about, one type of algorithmic output. So we want some notion of similarity that is going to work whether we're producing numbers or large sets of statistics or trained machine learning models or synthetic data. And somehow we need a notion of similarity that's going to work in all of these cases. If we can find this notion of similarity, what we're going to get from a privacy guarantee like this is basically that differential privacy can be thought of as a robustness guarantee, a stability guarantee of our computations. It's saying that our computations aren't very sensitive to small changes in their underlying data. And intuitively, from the individual's perspective, if they're thinking about whether to provide their data for a differentially private computation, the message to that individual is, well, your data doesn't affect the outcome very much. And that gives you a guarantee that can be interpreted as a privacy guarantee. In parallel, there's a requirement here, a guarantee that comes out of differential privacy that says any attacker, any observer who's seeing the results of these algorithms is not going to be able to get very much information about the content of any one person's data. If their data was in the input, they're not going to get much information about whether any one particular person was present or absent from the data set. And the goal is to get these kinds of strong guarantees, these robustness, stability types of guarantees about our computations, while simultaneously still retaining the underlying interesting stuff that we wanted to extract from the data, whether that was correlations or trends or aggregates, or the ability to train accurate models. So a little bit more formally, what differential privacy says, and this is one version of the differential privacy notion. There's sort of a family of different related notions, but this one captures most of what we want to talk about today. The idea is that formally for any two databases, D and D prime, that are identical sets of rows except for the addition or removal of one person's data, so one row from the data set, we want to constrain the behavior of our algorithms so that for any possible output of the algorithm, the probability that we get that output under database D is almost exactly the same as the probability we get that output under database D prime, that neighboring data set, and vice versa. So one of the things to notice here is we have an almost exactly the same probability that's parameterized by some e to the epsilon. So we have an epsilon knob. We have a knob that controls privacy here. And basically what that means is when we tune our epsilon very small, then these two probabilities are forced to be very, very similar to each other. So we're not allowed to have very, very different behavior on differing data sets. When we tune that epsilon higher, then those probabilities are allowed to differ more significantly, and we're allowed to have more significantly different behavior. This allows potentially for more accuracy of our algorithms, but worse privacy. But we have a knob here that we can tune that helps us understand more versus less privacy. Now, as I mentioned, the literature has really taken off over the past couple of decades, and we have lots and lots of different algorithms for achieving differential privacy. They work in many, many different ways, and I'm not going to get technical here, but just intuitively, we achieve differential privacy sometimes by noising the data, sometimes by noising the behavior of the algorithm. For example, adding noise to gradients when we're doing a gradient descent. Sometimes we achieve privacy by running the standard algorithm, the non-private algorithm, and noising its output. And sometimes we do things that look like something else entirely. So we have a really rich and diverse vocabulary of tools that achieve differential privacy. And those tools can be assembled into more complex algorithms that give us these stability guarantees. Now, that's the background I wanted to give us on differential privacy. But in some sense, what I really wanted to talk about is non-privacy. Because parallel to the algorithmic literature on differential privacy that's been evolving over the past couple of decades, that's given us this rich algorithmic toolkit, simultaneously a literature on lower bounds has evolved. And this lower bounds literature has taught us things about what's possible and what's impossible under any reasonable notion of privacy, not just differential privacy specifically. So if you have some gripe with the particulars of the differential privacy notion, that's fine. The point is that we have some really fundamental lessons that this literature has given us over the years about what's possible and what's fundamentally impossible, basically for any notion of privacy. One of the lessons here that comes out of this literature is that in some sense you can really only get aggregate information out of your data. But the lesson I want to focus on here is the lesson that privacy harms necessarily add up. So what do I mean by this? So every time we take a sensitive private data set and we do something with it, we do some computation, an aggregate statistic of some sort, a release of some sort, a decision on the basis of that data. Every single computation that we do on the basis of that data, its output forms a constraint on what the underlying data could have been. So even if all I do is take a data set and compute that 49% of the people in the data set identified as male, immediately I've learned a lot about the underlying data. Even if there was some noise in that 49%, it's all of a sudden extremely unlikely that a data set that's 23% male was the one that generated the statistic. And it's similarly unlikely that a data set that's 90% male is the one that generated the statistic. So every statistic, everything that we do that's on the basis of a data set that is useful in some way, is interesting in some way, provides a constraint on what the data set could have been. Without adding any noise to these constraints, if we think about outputting a sequence of aggregate statistics about a data set, then a basic observation is that about n statistics provide significant enough constraints on what the underlying data could have been that together they allow you to substantially reconstruct the underlying data. So if the data was a size n, about n statistics allow you to reconstruct the underlying data. And even if we add noise to those statistics, any statistic that teaches us something new is a new constraint, maybe a noisy constraint, but still a constraint. And those statistics add up. Those privacy harms unavoidably accumulate. And so even a sequence of seemingly innocuous aggregate statistics about a data set reveals something about the underlying data. And what can be revealed can add up quite quickly to allow us to recover the underlying data quite well. So these lessons about negative results that are not specific to differential privacy really inform what I think of as sort of the mindset of differential privacy. This mindset takes into account the fact that privacy harms unavoidably necessarily add up across data users, across data sets. Every time we do something useful and interesting on the basis of a sensitive data set, even if we add privacy protections, even if we add noise, those harms add up. They teach us more and more about the underlying data. And this shifts us to thinking about our use of a sensitive data, use of sensitive data in a way that has sort of a privacy budget associated with it. The idea here is if those privacy harms necessarily add up, then there's a limit to how many useful computations I can actually do on a data set before the risks of reconstruction, the risks of privacy harm are too significant for us to be willing to accept. And so there's a limit to how much I can use a data set if I care about privacy. And this is really, really fundamental, unavoidable, basically sort of a mathematical fact, regardless of how you want to define privacy. Now, the idea that privacy harms add up, or more specifically, that multiple observations about a data set can combine to provide more than the sum of their parts, is not new. So some of you may have encountered at some point the term mosaic effect. This is a term that's used in part in the intelligence community. It also appears in certain places in US law and probably in other places as well, to refer to how fragments of information that individually seem really meaningless on their own can somehow together produce a detailed and useful picture. So the mosaic effect is sometimes a term that's used to justify withholding information, for example, on the part of the government in response to freedom of information requests. And there, the concern is maybe balancing the need to protect national security and the right of citizens to access information. The mosaic effect also has been referenced in the context, for example, of the US Fourth Amendment to balance the government's need to access citizens' data for law enforcement against citizens' reasonable expectations of privacy. And basically, the argument behind the mosaic effect is that sometimes all the little data releases that each seem totally innocuous on their own sometimes add up to give a too clear picture. And that too clear picture can risk national security, it can violate individual privacy, and then that can be a reason to limit those little seemingly innocuous data releases. So this shows up in lots of places, as I mentioned. In particular, it shows up in two memoranda on US government data sharing, in particular about US data sharing with outside parties outside the government. And both of these documents that I'm referring to here explicitly refer to the mosaic effect. When the release of an individual data set may not risk disclosure of private information by itself, but where it could lead to disclosure if it were combined or viewed against the backdrop of other data releases or with other publicly available information. So these policies are an explicit acknowledgement of the ways in which privacy harms add up and sort of provide an obligation to think hard about how these things add up. But I want to say that what differential privacy's perspective gives us is something that's a little bit more, something a little different than what the mosaic effect typically has been used to capture. Because part of what's missing with that mosaic effect approach is that it only talks about accumulated harm from data releases. So typically the language of the mosaic effect is, if I release this data, these facts, these measurements, then it seems innocuous, but maybe against the backdrop of other facts, other measurements, it could be harmful. But one of the things that differential privacy teaches us is to be concerned not just about data releases, but about how data uses accumulate. So by a data use, I just mean a release based on data such that the output would differ if the data set were different. But this could be a release that looks much more like a model that we train on a data set, or the set of statistics that we publish on the basis of a data set, or the insights we generate, or the trends that we extract that together inform our policies and our actions. All of these are data uses, and these data uses also constitute information about the underlying data. They constitute privacy harms, and they also add up the same way that sort of more traditional data releases add up. So I'm going to say data degrades with use as shorthand for this idea, but I really mean that there's a limited number of times that we can make useful use of a data set while respecting the privacy of its participants. So here we arrive at the bottom line for privacy. Privacy concerns mean that data degrades with use. Every computation on a data set that has downstream visible consequences is a privacy leak, period. Even with the best technology, the best protection, everything you could possibly put in place, if those computations have any meaning, they harm privacy. Those harms unavoidably accumulate. And so if we want to give individuals meaningful overall privacy guarantees, every computation in some sense should be thought of as a foregone alternative computation. Because you have a budget, you have a limit to how many computations you can do. And your use of the data set now potentially harms my ability to use it because we're spending from the same budget if we're both making the results of our computations visible in some way. So when privacy is a consideration, I assert that regulation should make data use a rival good. What do I mean by a rival good? So a rival good is a concept from economics. It dates back to the 70s. The idea is a rival good is one whose possession or consumption by one consumer interferes with its possession or enjoyment by other consumers. When we talk about rival goods, we usually talk about things like if I'm eating the apple, you cannot also eat it. If I'm wearing the scarf, it would be awkward if you were also wearing it. If I'm sitting in a seat on an airplane, I really hope you try not to occupy it at the same time. These are rival goods that can't be enjoyed by multiple customers. And the idea here is that we want, in some cases, to make data a rival good because we want to respect this privacy budget, this sense in which we have a limited amount that we can use data. We want my use of the data to interfere with your use of it. But that's something that doesn't happen on its own. It's something we have to impose. It's not that you're sitting in the seat, so I physically can't sit there, because with the data, if you're using it, nothing forces me to not be able to use it. But somehow we would like to create an infrastructure that would cause this rivalrousness to be visible and for us to experience it. And this is in direct contrast to a lot of literature that talks about data as explicitly non-rival. Now, again, to dig into this rivalrousness a little bit more, the point that I'm trying to make here is not that me using data sometimes makes other people worse off. That's kind of an obvious point about negative externalities. It's not very surprising. The point is that my use of data should, at least sometimes, make others worse off in a very specific way. It should make others worse off by making that data or other related data less useful to them because I'm spending from a collective budget of data use, and that gets eaten up. This rivalrousness that we need in the context of using sensitive data induces a need for new technologies, and it raises a lot of questions. If privacy harms unavoidably add up, somebody has to track them. Who? How? With what infrastructure? It encourages us to potentially redesign our learning infrastructures, to more strategically think about when we use data, how we use data, how much data we use, how accurate we really need our results to be. Because all of a sudden, every computation costs something in a new way, and we want to be judicious in our use of the data. It raises some really tough questions. If there are multiple potential uses or users of a single data set, now all of a sudden they're competing over the same privacy budget. And all of a sudden we need a language and mechanisms for deciding whose computations get prioritized, whose get done. There are questions also about who gets what level of accuracy, because more accuracy spends the privacy budget faster. That's that privacy knob we saw in the context of differential privacy. So all of a sudden now we have to have some competition, some fight, some negotiation, something around what computations get done. And this is going to require us to talk and to reason about the value of particular uses of a data set. One might hope that this is just a pricing problem. Maybe we just need markets to address the situation. But I'd say that the caution is warranted. We might not want to live in the world that would emerge if it were just money that decided which computations are used on our sensitive data. Okay. Now, forget about privacy. You don't care about privacy anymore. All you care about now is doing good science on data. Okay. What I want to claim is that science is inherently, necessarily, desirably extremely adaptive. Adaptivity, what do I mean by this? I just mean the idea that the hypothesis I explore, the question that I ask, the measurement that I take today is often informed by things I've learned in the past. So I might notice a pattern in the data. I might then go and explore it further. There might be some shared genomics data set used by many different research groups. I might read a paper from one research group and from that get some inspiration for some new study that I want to go and run on this data set. Or maybe I might have a huge set of possible variables. I might do something to identify promising variables and then leverage them and evaluate them. All of these are instantiations of adaptivity in science. And I'm about to give us some warnings about adaptivity in science, but first I want to say adaptivity is great. Adaptivity is wonderful. Adaptivity is necessary for doing good science. If we didn't have adaptivity, we would collectively have to write down all the scientific questions we might want to ask in advance and just ask them one at a time in order, without being able to leverage the fact that we learned that there's nothing promising over there, or hey, wow, there's some interesting phenomenon over here. Let's go take a look. Adaptivity is really crucially essential to making meaningful scientific progress, but adaptivity can and does often get us into trouble, particularly adaptive reuse of the same data set. So we see this in many, many ways, in many fields. We see evidence, we see attributed to adaptivity all sorts of scientific woes. Maybe you've heard over the past decade and change about some reproducibility crises in a number of data-driven social sciences. There have been large studies that attempted to reproduce not just sort of minor, but really important, groundbreaking, well-published results. And it found that many of them don't replicate. And one of the factors, not the only factor, but one of the factors that's blamed here is adaptive reuse of data. This is sometimes referred to as the statistical crisis in science, that many of the results that are being published on the basis of data do not come with meaningful statistical guarantees and may not replicate on a fresh sample, or may not be reflecting sort of the true behavior of the underlying data. Now, this is something, it's tempting to say, oh, that's the problem of those social scientists over there, but it's a phenomenon we also see a little bit closer to home. So maybe you're familiar with the notion of a Kaggle competition. The idea here is I want to outsource the discovery of really good new models for my particular type of data, for maybe doing some sort of prediction task. So I'm going to set up a Kaggle competition. What I'm going to do is I'm going to bring a large data set. I'm going to split that data set into 3 pieces. And I'm going to make one piece of the data set basically public. Anybody who signs up for my competition, do with that data anything you want to. It's yours to play with, explore, try all your models, go wild. The second piece of the data set is held back. And that piece of the data set is used to run a leaderboard. So periodically, if you think you've got an interesting new model, you can submit it, and we'll score it on the basis of that second data set that you've never seen, and use that to place you on some running leaderboard as we're running the competition. And then finally, once the competition has closed, we pull out a third data set that nobody has interacted with so far, and we use it to score the winners and determine the winners of our competition. And the interesting fact is that we see evidence that competitors overfit to the second data set. Now, that's a data set they didn't have their hands on, they didn't have access to. Their only access to the second data set was through this interface of submit a model, get a score. And they had no incentive whatsoever to overfit to that second data set. It doesn't help you to overfit to the second data set. And yet we see evidence that competitors overfit to the second data set, which causes a reordering of the leaderboard when we actually move to the final winners, and we actually score people on the third held out data set, where there was no contact with the data set whatsoever. So this is some evidence that even a little bit closer to home, we have a tendency, even when there's no incentive to do so, to overfit to data, even data that we don't have our hands on directly. So what's going on in all of this? The issue is that repeated adaptive use of the same data can mislead us. It can mislead us intentionally. It can mislead us unintentionally. What it can lead us to do is to focus on sort of quirks of the data sample that it turns out don't manifest on the underlying data distribution. It can be difficult when you find something interesting in your data set to know whether or not that's a phenomenon that would actually show up in a fresh sample of the data. Now, setting aside adaptivity for a moment, I want to observe that science on a sample works amazingly well. Our ability to draw a sample from an underlying distribution, do science on it, and get conclusions that have meaning for the underlying distribution is enormous. It's fantastic. As long as you're not adaptive, if you make your list of scientific queries and hypotheses and measurements all in advance, and you fix it in advance and you write it down on that scroll, and then you run it, a simple Chernoff bound and a union bound shows us that we can answer a number of non-adaptively chosen queries that grows exponentially in our sample size. So we can do a ton of non-adaptive data and get amazing guarantees that with high probability, all the answers to all the queries that we issue will be accurate with respect to the underlying distribution. That's really amazing. We have to appreciate that for a moment. We can do a huge amount of science on a sample. The problem is, as soon as we have adaptivity, that all goes out the window. As soon as our queries are chosen adaptively, in the worst case, we can overfit terribly on the second query. So instead of exponentially many queries, we get one and then we overfit. This is a disaster for science because we want that adaptivity. Now, this raises the question of how should we be doing science on a data sample? And one solution is forget about adaptivity. Give it up. Don't reuse your data. The problem is, of course, data is expensive. Data is valuable, whether it's hand-coded or there's a limited amount of it or whatever the reason. And in many cases, you don't want to have your database size grow linearly with the number of rounds of adaptivity. You want to be able to think and learn and reuse. Okay, so let's spend a couple of minutes modeling this adaptivity problem so we can get some insights about what's possible here and what it teaches us. So basically the setting is one where we have some data domain. We're going to have access to a particular data set of size n from that domain. And we want to design algorithms, we'll call these mechanisms M. They're going to take in a database. They're going to receive a stream of queries. These are questions about the database. And then are going to return a stream of responses, these R's, these answers in response to those queries. And basically, where are those queries going to come from? Well, in our adaptive setting, they're going to be generated by some analyst or maybe adversary. The A is a convenient letter for us here, that gets to choose those queries, not just sort of fixed in advance, but potentially based in part on the past query response pair. So they have access to this past stream of responses when generating the future queries. So we have this interaction now between a mechanism that's answering questions and an analyst that's providing those questions. And those questions are potentially being generated adaptively. And what do we want? We want to, in some sense, be able to put a box around this interaction and be able to say, here's a box. If you feed in a database, you feed in a mechanism, you feed in an arbitrary adaptive analyst, we're going to get a guarantee that this box is going to output a sequence of queries and answers that has good properties. What do we mean by good properties? Well, that those answers are going to be good for those queries, not just with respect to the data set we have on hand, but if that data set was drawn from some underlying distribution, we want those answers to those queries to be good on the underlying distribution. This is the adaptivity problem. Now, there's been a really nice line of work starting with a paper of DeWork, Feldman, Hart, Patassi, Reingold, and Roth about 10 years ago that really helps us formalize and understand the sources of adaptivity's harms. And in some more recent work, joint with my PhD student, Moshe Schenfeld, one of the things that we show is a very simple sort of fundamental theorem that characterizes how adaptivity gets us into trouble. I'm going to say it in words here, but the actual mathematical theorem is not so much more complicated than this. It basically says two things both need to go wrong in your scientific pipeline in order for you to be misled by adaptivity. The first one is that your previous query's answers have to encode a lot of information about your data sample, as opposed to about the underlying distribution. And the second thing that has to go wrong is that subsequent queries actually have to leverage this information in order to overfit. So we use this characterization of how adaptivity can mislead us to give us improved algorithms that help protect against adaptivity's harms, to develop new ways of designing a scientific pipeline that allow us to issue adaptive queries, but to give formal, rigorous statistical guarantees about the validity of the answers that we're going to get, not just on the data that we have on hand, but also with regard to the underlying distribution that we care about. So a little bit more intuition about how this sort of reasoning works. What's the goal here in this world? The goal is we want the answers that our mechanism gives to the queries that it receives. I put that in the bottom left corner here of the picture. They're not too far from the answers to those queries on the true underlying distribution. I put that in the top box there. And so we call this relationship, these two things being close to each other, distribution accuracy. That's what we want. We want our answers to be close to the answers on the underlying distribution. Now, how can we get this sort of a guarantee? One might try to get this relationship by arguing some sort of triangle inequality. And one natural one that you might initially think, okay, maybe this is the algorithmic path forward, is the following triangle inequality. Maybe we could somehow guarantee that the only queries that get issued are queries whose answers on the sample are close to their true answers on the underlying distribution. That would mean that those queries in some sense generalize. That's that right side of the triangle. And then if we designed our mechanism to give answers on those queries that are close to the answers on the sample, we'd be done. We only asked queries where the answers on the sample are close to the true answers on the distribution, and then we just have to give answers that are good with respect to the sample, we'd be done. But it's not clear how to achieve this. It's not clear how to algorithmically get this guarantee using this type of a triangle argument. So it turns out that the literature has developed an alternative sort of sequence of reasoning, a different triangle argument that shows how we can achieve this goal of distribution accuracy through this other triangle inequality. So here we've changed out the bottom right corner of the triangle. It's no longer the value of the queries on the data sample, but now it's the value of those queries on some Bayesian posterior belief that's induced by the query answers so far. Don't worry too much about the details there. So it turns out that giving not too noisy answers with respect to the sample preserves not just sample accuracy, but also the necessary, what we're going to call posterior accuracy, for getting accuracy here on the bottom edge of this triangle. And then the twist, the surprise character that reappears in the talk at this moment, is that differential privacy ends up being a tool that gets you the posterior insensitivity that you need for this right-hand side of the triangle. Because it turns out that differential privacy, as a stability notion, as a robustness notion, prevents our query answers from encoding too much information about the data sample, so that you're prevented from subsequently selecting overfitting queries. So basically, if you inject a little bit of noise, differentially private noise, to your interaction with your data set, to the answers you get to your queries, to the models you train, and so on and so forth, that actually can give you formal guarantees that you're prevented from overfitting. And now all of a sudden it unlocks more repeated adaptive use of data than we would have had access to without this noise, without this differential privacy alone. There is a lot more to say here. It turns out that the noise levels that are induced by differential privacy are necessary in some worst case situations, but they're overkill in others. And there's initial progress and a lot more to explore. But the point that I want to make here is that adaptivity makes data use more rival. Adaptivity, whether that adaptivity comes from human scientists or from AI scientists who are surely adapting at breakneck speed, optimizing like crazy against whatever goals we've set for them, adaptivity in our scientific pipeline, which we want, which is necessary, which enriches our ability to squeeze more out of our data, comes with a risk, because every computation necessarily, even with those that noise that we add, reveals more information that could be specific to the data set as opposed to the underlying distribution. And those revelations add up. So if you want to protect the world from being able to ask overfitting queries, you want to build a rigorous scientific pipeline that uses adaptivity and maximizes the amount we can squeeze from our data, then you have to think a little bit about, in some sense, a statistical validity budget that gets spent every time we use our data set. And your use of the data set can mislead me, and it in some sense degrades this common budget. Now, this is a wildly different way of thinking about data. It's not the kind of thing we'd think about if data were a non-rival good. And generally, when we're thinking about data for science, we think more use is better, more sharing is better. But this suggests the need for some more caution, maybe some new infrastructure in place that might help us think about how do we track data uses, how do we track data sharing? Do we want to provide some limits there? Do we want new infrastructure to maybe detect adaptivity-driven harms? Do we need to do more work to build the pipelines that will preserve the quality of science, particularly as more and more is automated with AI? So, in summary, we've seen two different perspectives that suggest that maybe we're not always entirely in this data fire hose world where you can use whatever data you want as much as you want and share it as much as you want with no consequences. Sometimes data is still plentiful and should be used and freely shared, but things are changing and the perspectives that we need to bring are a little bit more subtle today. And there are lots of reasons for this and lots of justifications. Maybe these days we're more in this world where we get these kinds of headlines claiming the data is all of a sudden scarce, the data is being used up. Now, even though the reasons that AI is using up all the data are somewhat different than the issues we explored in this talk, some of the themes and the consequences and the questions that it raises, I think, are really closely related. And the general lesson, I think, is that our model and our assumptions about data matter, and they're not universally fixed. And perhaps at least sometimes data is best thought of as a resource that is depleted as it's used. And this is a really major shift in our thinking. To think about data is disintegrating as we use it. And that perspective, when it's relevant, demands innovations and raises questions of all sorts. The set of questions here is extremely, extremely rich. Just a quick sampling. There are a large number of questions that are raised here around reduction of our use of data, or more cautious use of data, more judicious use of data. Maybe we need to try to shift to algorithms that really use only what they need. They touch only what they need. They minimize spread. They minimize sharing. They keep track of the spread and the sharing of data. Maybe this suggests a shift to more significant use of synthetic data in some settings. But then we need a much richer vocabulary and toolkit and understanding of what is synthetic data. How do we create it? What can it do? What can't it do? How do we give guarantees about it? And how is it potentially serving our needs and promoting our ability to squeeze more out of our limited data resource? This whole sort of headache around my use of data degrades the data for you raises all sorts of coordination questions and coordination problems. This all of a sudden demands potentially some sort of deep awareness of others' use of the same data or of related data. And that's potentially, even if the other is not just within my organization, but somewhere else entirely. It suggests that maybe in some cases we need much more explicit tracking and coordination of data uses. It suggests that maybe we need to set up systems that allow us for some sort of budget and some sort of negotiation over that budget. But it raises a lot of questions about who has a right to that budget, who has rights in our collective data or in a particular group's data. What do those rights look like? Who decides how that data gets spent? Because it's something that we spend, it's something that's budgeted, it's something that's limited. Who decides what computations get prioritized for accuracy or for execution, and which computations are set to the side? And this raises all sorts of challenging questions. In the context of scientific pipelines, we have new questions about what do we need in terms of maybe a shared replication infrastructure to help us build better scientific results, a better scientific infrastructure, because science is built on the shoulders of those who came before us and the results of those who came before us. And if those results are not reliable, if they're not going to replicate, we have serious problems. So how do we build a replication infrastructure that makes the best possible use of our limited data resources? There are also huge questions around incentives that are raised here. In the context of science, these are questions maybe about, do we need to change publication incentives? What do we need to require from authors? Many journals in certain fields have been requiring explicit data posting and data sharing. Is that actually good for science? When is that good for science? What are the pros and cons of these approaches? What are we rewarding in our publications? Are we not putting enough emphasis on negative results? Are we somehow skewing and creating bad incentives for authors that are contributing to our failure to replicate downstream? You might think in the context of privacy or otherwise about maybe assigning penalties in some way, but where do those penalties come from? Do they come from academic institutions if we're thinking about privacy? Do they come from governments? Penalties for privacy irresponsibility, because in some sense, you're wasting a shared resource when you are being privacy irresponsible, whether that's asking sort of not very useful or important questions or doing something else that degrades the privacy of a data set. Should we be penalizing a scientist who's issuing overfitting queries in some way because they're polluting the scientific landscape? How do we build infrastructure that supports innovation and competition? I think this is a really important set of questions, because I'm now coming and saying we have a problem. Data can't just be freely shared for innovation and for competition purposes, at least not always. But data has been really seen as a key engine for innovation and for competition. So how do we set priorities there? How do we make decisions? And then there are the huge questions around incentives for data creation and provision. If data is a limited resource that's degrading with use and it's a valuable resource, we need to think about how do we ensure that we have good supplies of data? Who is generating that data, and how do we ensure that it's high quality data that's being generated? So I hope this talk offered some challenging directions and some food for thought that you'll take into your own research. And I hope that you'll look at data a little bit differently going forward.
Thank you very much, Katrina. It was a very, very good and interesting talk, inspiring. Yes, so any questions from the audience? Okay, so I want to start. I have a few. Actually, I mean, oh, sorry. Apparently I didn't. Okay, you can see me now. Okay, so the audience is welcome to send us some questions, and I'll start. So in your talk, you, I mean, I saw it as divided to, two main parts, except from the last one where you raised a lot of questions. In the first, you addressed privacy, and in the second, you addressed statistical and scientific validity. So actually, my question can be divided to two. First, it's surprising that differential privacy is like a solution to both problems. Is it like something that you considered? Like, is it the same type of solution that can be adapted to, address both kind of problems? Is it something that you see as, a kind of a toolbox that should be adapted to, machine learning solutions and things like that? There was like a very tight connection here, so it was surprising, actually.
Yeah, so I think that this is a really great point. And part of what's going on here is that the privacy notion of differential privacy can be interpreted not just about as a privacy notion, but also as sort of a stability robustness notion. And when you put it in that language, maybe it's not as surprising that ensuring that the results of our computations are robust to small changes in the underlying data, that is also a protection. It's a protection not just against revealing the details of those individuals, which is sort of the privacy interpretation, but it's a protection against encoding the details of that data sample in a way that potentially harms us with regards to overfitting. So being robust to small changes means that we're learning in some sense the aggregate trends, the sort of important messages overall that the data set has to offer to us, and we're not fixating on the details. So in that sense, it's not so surprising, but it is true that what we need for privacy and what we need for statistical validity are not exactly the same thing. Okay. Privacy is necessarily inherently a setting where we want to be super, super, super paranoid and worst case, because we want privacy for the weirdos and the outliers, the ones we don't think are ever going to show up in our data set in some weird world. We want to protect them. Whereas when we care about statistical validity, we care about the data set that we have on hand. And we care not just about a worst case computation, but we care about the computation we have at hand. And we don't necessarily need a guarantee that holds in the worst case that's unlikely to manifest. Maybe we need a guarantee that holds with reasonable probability in the situation we actually face. And so it turns out that for that reason, that although the toolkit of differential privacy for robustness, the mathematical framework is extremely useful and portable and does give great insight into the statistical validity problem, it's sometimes overkill. And sometimes if you add noise according to what differential privacy would dictate, you're adding more noise than you would need to, because you don't really need to protect the worst case. And what you care about is this sort of scientific guarantee of validity.
Yeah, an interesting, like, just a remark is that I used to see those two notions as competing, right? Privacy and scientific validity. I mean, the more you obscure, the less you know. But here it's the opposite. So actually, they are aligned in the sense that data usage sense. So it's interesting. One other question that you didn't like talk about, a practical application of that. Is there any practical solution where this has been addressed with a well-known data set or something that we can use as a solution?
So the statistical validity toolkit is still, in some sense, I think a couple of steps short of being really practically deployable. The theory that's in place is very much a theoretician's theory without a lot of sort of work to squeeze the constants, and without a lot of thought so far about this sort of non-worst case scenarios. And so there's a gap there that needs to be filled sort of both from the practical side and from the theoretical side to get us to the point where this is something that's going to be really highly useful and deployed. But I think that sort of AI-driven science really offers an important setting to be thinking about these tools, because all of a sudden our science is happening at a new scale, at a new rate. We're dealing with huge data sets, potentially extremely rapid and kind of unpredictable in some sense levels of adaptivity. And so there's an opportunity here, I think, to leverage the insights so far from this theory, but to really try to build it towards something that is more explicitly practical.
Thank you. Thank you very much. So there's the questions from Dick Battleman. Can you send it over? Okay, so the question goes like that. So, Katrina, thanks for the talk. Is still hungry for some example that help me understand how the data degrades in practice.
Right, yeah. So maybe we'll go to an example that comes from the United States Census. So the United States is obligated every 10 years to gather information about every single person who resides in the United States. And simultaneously, the census is an extremely valuable resource. The census data that's gathered is used for all sorts of decision making, for allocation of all sorts of resources, and it's the basis of basically all sort of scientific and social scientific understanding of the US population. So this is really foundational work, this foundational data that's being gathered. So the census is required to gather this data. They also have an obligation not to reveal anything that could cause the individuals in that census data set to be re-identified. So they have a privacy obligation, but they also have this data gathering and data sharing obligation. And every year, every census, billions of statistics are released by the US Census on the basis of the census data. So it's a huge number of statistics that are released. After the 2010 census, the census became concerned that maybe the privacy protections they were putting in place, despite being sort of state of the art, were insufficient. And so they actually ran an attack on themselves. They tried to see how the statistics they'd released on the basis of the 2010 census could be used to recreate the underlying census data. And they had an extremely successful, unfortunately, extremely successful attack. And they realized that those seemingly innocuous statistics, things like, how many males between the ages of blah and blah live in Alabama, things that look totally innocuous, once you have enough of these aggregate statistics, they constrain the underlying data in a way where you can do incredibly accurate reconstruction of the data of the majority of the US population. So this is sort of a disaster that really illustrates how these individual innocuous statistics add up in practice.
Super interesting. It seems that you could talk about it forever. Any more questions? Yoel?
No, we're just on time. So and I think it's awesome that we could. We're just on time. So thank you so much, Katrina. Fascinating. Yeah. And thanks, Dick and Liam, for the last question, because that was mind-blowing. So thank you so much, everyone. Now we are going to, you're going to have a well-deserved break for about almost half an hour. We hope to see you back on the platform. And again, big kudos and thank you to Katrina for an awesome presentation.
Thank you very much.